This video covers identities from section 4.2 in our textbook, and what you're looking at here is the upper part or first part of a document that covers both the 4.2 and 4.3 identities. Of course, I'm only zeroing in on the 4.2 for now. The 4.2 identities are for the sum and difference identities of cosine. That's right. And so you can see them here near the middle bottom of your screen. I'm going to read them and then discuss just some similarities with them to help us memorize them, and then we'll see plenty of examples using them. The first one reads, the cosine of a plus b equals the cosine of a times the cosine of b minus the sine of a times the sine of b. Of course, the second one reads similarly but different, cosine of a minus b equals cosine of a times cosine of b plus sine of a sine of b. Now, I would like to point out some little tricks that might help us remember what these are, because they do need to be committed to memory. The first thing is this. Notice how incredibly similar these two different identities are. In fact, if you look at it carefully, you'll notice there's only one difference, which is the sign in between the terms originally. So cosine of a plus b, notice the plus sign there. And then notice that between the terms on the right side of that equation, you have the opposite of that sign, which is a minus. In the second equation, of course, this one is for the cosine of a minus b. Notice between those two terms is a plus sign on the right side. So you'll notice that the signs are the opposites from what you see on the left and right side of these equations. Otherwise, the formulas or identities are identical here. Notice it's cosine A, cosine B each time in the beginning, first term, and then plus or minus depending on the sign, and then sine A, sine B. Those match for the second terms. Let's take a look at an example to try to apply some of these cosine identities. And the first example reads as follows. Find the exact value for the cosine of negative 195 degrees. Now, it doesn't take too long to figure out that 195 degrees is not one of our special arc lengths on our unit circle. Because of that, we're going to have to use some other tricks, knowing that we want an exact value. You see, calculators can handle these kinds of problems usually, but they often give a rounded decimal, or a decimal that we would have to round. But an exact value means we do not want a decimal for the answer. So, since cosine of negative 195 is nothing on our unit circle, we're going to have to use some identities to break this down. Let's go ahead and just copy down the expression we're starting with, cosine of negative 195 degrees. The first thing I want you to notice is this negative sign right in front of the 195. Hopefully this makes you think of one of the basic identities that we started with in section 4.1, which is the negative identities. For instance, you might recall that, I'll put this in quotes over here, that the cosine of negative x is equal to positive cosine of x. That's right, so this is the negative identity for cosine. There's no negative sign in front of the right side for that identity. So, applying that identity to this example would tell us that the cosine of negative 195 is the same thing as positive cosine of positive 195. That's right, they're no different according to that identity. That takes care of the negative sign, but now the 195, like we said, is not on our unit circle. So what we're going to have to do is try to use the sum or difference identity for cosine and split up 195 and try to do so using special angles that are on the unit circle. For example, can you think of two angles in degrees on the unit circle that would add to 195? How about making this equal to cosine of 150 degrees plus 45 degrees? You see, both of those degree marks are on our unit circle as special arc lengths or degree measures, and so we can find their exact values with no problem. Furthermore, of course, 150 plus 45 is 195, so we really haven't changed the problem on us yet. Now, the whole point of this is that if we can make this match up with our angle identity, our sum or difference angle identity, which of course this would be a case of the sum, where we have cosine of A plus B. So in other words, A is 150 and B is 45. And if we can use the identity and substitute those values in, we should be able to evaluate this with no problem. So follow along with the cosine sum of angles identity we had listed in the very beginning of this video. It's on the handout for section 4.2 identities, as we replace the A and B with 150 and 45. So we'll end up with the cosine of 150 times the cosine of 45, and then we're going to use the opposite of the sign we have, which is a plus. Here we used a sum, so I'm going to say minus, and then we use sine of A, which is 150, sine of B, which is 45. Alright, so that's just a direct replacement using the cosine identity for sum of angles, A plus B, and replacing A with 150 and B with 45. Now we can evaluate these using our unit circle values. The cosine of 150 is negative root 3 over 2. The cosine of 45 is root 2 over 2. So I'm just substituting those exact values in for the special arc, in this case degree measure unit circle values. Moving on to the second term, the sine of 150 should be 1/2, and the sine of 45 should be root 2 over 2. So we've converted every term or every factor to an exact value. All we have to do lastly is multiply these together to simplify. By the way, if you're having trouble remembering some of these unit circle values, that may be a good indication that you might want to review the unit circle, because it's not going away. We're going to have to use those values often here. Let's now simplify by multiplying these first two factors together. Of course, negative times positive is negative. Now, remember what you have to do with roots. We have root 3 across times root 2 on top here. So you might remember that when you multiply radicals together, which you can do, they have to be the same radical, which they are. They're both square roots. And then to do so, you just multiply what's underneath each radical together. So 3 times 2 is 6. And then we'll multiply denominator with denominator, 2 times 2 to get 4 for that denominator. Let's move on to the second term. Of course, we'll be subtracting here. Similarly, on top, we'll have 1 times root 2, which is root 2. And down below, we'll have 2 times 2, which is 4. Now, we can finish with a common denominator, which we already have in place here as 4. But there's not a whole lot we can do with the numerator. Only like radicals can be added or subtracted, and like radicals have to have not only the same root, meaning both square roots, but also the same radicand, which is the part underneath the root. And so since 6 and 2 are not the same, we cannot combine those in any way, which means we'll leave our answer as simplified as can be as negative root 6 minus root 2 all over 4 the LCD. Let's look at another example where we want to evaluate the cosine of 5 pi over 12. Now, notice once again that 5 pi over 12 is not a unit circle special arc length of any kind. So, similar to the last problem, we're going to try to come up with a way to represent 5 pi over 12 that uses the special arc values that we do know on the unit circle. So this will take just a little fraction work, but let's see if we can split this up. And by the way, we could use a sum or a difference, and there often are more than one ways to handle these. Let's think through this. Couldn't we write cosine of 5 pi over 12 as the cosine of 3 pi over 12 plus 2 pi over 12? According to basic fraction arithmetic, these have an LCD of 12, so adding them together, 3 pi plus 2 pi would give us 5 pi. So indeed, those are equivalent, and furthermore, we can reduce each one of those to special arc length values. So 3 pi over 12 is the same thing as pi over 4. That's simply because 3/12 is 1/4. And then 2 pi over 12 is the same thing as pi over 6 for the same reason. 2/12 is just 1/6. And so here we go. We have pi over 4 and pi over 6 both of which are nice special fraction values. Let's go ahead and apply our cosine sum of angles identity and rewrite this to be cosine of first angle, which, remember, this first one is kind of like A, and the second one is kind of like the B if you're matching up the formulas there. So cosine of A plus B is cosine A, which is pi over 4, times the cosine of B, which is pi over 6. And then we use the opposite sign, so if this is a plus to begin with, we're going to use a minus here. And then we do sine of A and B, so sine of pi over 4, and then sine of pi over 6. So there's the direct replacement into the identity. All we have to do now is rely on our unit circle to convert all of these to exact expressions. So the cosine of pi over 4, of course we know this, is root 2 over 2. Cosine of pi over 6 is root 3 over 2. Moving on, the sine of pi over 4 is root 2 over 2. And the sine of pi over 6 is 1/2. Alright, now we'll just simplify with a step or two here. Similarly, we'll multiply the numerator with numerator. These are radicals, so root 2 times root 3 would be square root of 6. Denominator is 2 times 2 would give us 4. And then second term would be minus here. Root 2 times 1 is root 2. And then all of that is over 4. So then with an LCD, we'll combine these. Again, we can't put the roots together, but we'll leave it as the square root of 6 minus the square root of 2 all over 4. Let's look at another example. This time we want to find the cosine of, and then we have some brackets holding a whole bunch of stuff inside here, which is arcsecant of 2 plus the sine inverse of negative root 2 over 2. Now we're going to have to break this into pieces, otherwise it's a bit overwhelming to look at all of this at first. So let's take a look at what we're really seeing, which is that it's a cosine of something plus something else. Can you tell that this first arcsecant of 2 we could call perhaps A, and then the second term, the sine inverse of root 2 over 2, we could call that B. And if we do, this is really just the cosine of A plus B, which sounds hopefully familiar. We're going to use a cosine sum of angles identity for this. But then we're going to have to do a little bit of work to figure out what A and B are. So let's kind of take this into a couple little sideshows. First of all, if A is this arcsecant of 2, we can do a little bit of work to find A here by, first of all, let's take the secant of both sides. This would give us that the secant of A is equal to 2, and the secant of A, of course, is really 1 over the cosine of A, so that must be 2. But then if I want to get cosine of A on the numerator, I could just flip this entire proportion upside down to make this cosine of A equals 1 over 2. I'm flipping the left and the right sides of this proportion upside down. So cosine of A is 1/2. Okay, now let's also rely on what we know about arcsecant. You see, the range of arcsecant is from 0 to pi over 2, but not including it, and then from pi over 2 to pi, but not including pi over 2 on either side. So it's this upper half of our unit circle, but not including pi over 2. So I left a little bit of a gap there just to remind us. Now, if that's what we're dealing with for the range of arcsecant, that means that's where A could be, anywhere in that range. But if we know that the cosine of A is positive 1/2, that narrows it down for us. You see, positive for cosine is only quadrant 1, and of course 1/2 would occur up here at pi over 3. So this tells us that A must be pi over 3, just based on what we know from the range of arcsecant and the unit circle already. Let's move on and do the same thing for B. We can say that B must equal the sine inverse of negative root 2 over 2. Let's apply the sine function of both sides, so that we have sine of B equals, and the sine of sine inverse cancels, giving us just negative root 2 over 2. But again, we want to know exactly where on the unit circle this occurs. So if we can recall the range of sine inverse, which is the same as arc sine, this is negative pi over 2 to positive pi over 2, including each boundary. So we're right over here in basically the right side of the unit circle. This again is the range of arc sine. And so all we need to know is that if sine of b is negative root 2 over 2, that must be quadrant 4. And root 2 over 2 is the mark right in the middle. And so this tells us that b has to be negative pi over 4. That's exactly where we get to that place within the range of sine inverse. All right, if we know what a and b are, and remember, we designated a and b to be these original expressions inside our cosine function. Now that we know a and b, we can rewrite our original expression that we wanted to find in terms of a and b, and then just apply the sum of angle cosine identity. So instead of writing cosine of a plus b, which we originally used up here with a and b, we know that that's the same as the cosine of a times the cosine of b, and then we use the opposite sign, so minus the sine of a times the sine of b. And now we'll just replace all of those, knowing the angles a and b we found a moment ago with their respective values on the unit circle. So the cosine of pi over 3 would be 1/2. The cosine of negative pi over 4 would be root 2 over 2. So again, these are just unit circle values. The sine of a being pi over 3, would be root 3 over 2. And the sine of b being negative pi over 4, would be negative root 2 over 2. And so we can put this in simplified form by getting a common denominator as we've been doing, and end up with root 2 minus root 6 all over 4.